Subscribe to the channel so you don't miss out on any of these videos. In the vast expanse of space, with its countless stars, planets, and moons, a particular type of cosmic formation continues to captivate scientists and enthusiasts alike: planetary rings. As we peer into the heavens with increasingly advanced technology, the mysteries surrounding these enigmatic structures grow ever deeper. What are planetary rings exactly? How do they form, and why are they present around certain celestial bodies while entirely absent from others? These questions lead us to explore not only the intricate nature of ring systems, but also the cosmic processes that drive their existence. Today, we'll delve into the scientific depths of planetary rings, venturing beyond the basics to uncover the latest discoveries and theories, the complex mechanics that govern them, and the secrets they may hold about the evolution of our solar system and potentially others beyond. In the search to understand planetary rings, we must first look to the most prominent examples in our own cosmic backyard. Saturn, the sixth planet from the Sun, is an icon of ring beauty. But Saturn is not alone in possessing rings. Jupiter, Uranus, and Neptune also host ring systems, albeit far less prominent. Some scientists even suspect that planets beyond our solar system, exoplanets orbiting distant stars, may host rings of their own, potentially larger and more spectacular than any we've seen here. This leads us to question: why do rings appear around certain planets and not others? Is there something unique about gas giants that predisposes them to develop ring systems? Or could there be undiscovered mechanisms that account for their formation? The mystery of planetary rings is deeply intertwined with the science of orbital dynamics and celestial mechanics. In simple terms, planetary rings are vast, flat regions of particles orbiting around a planet, consisting of everything from icy chunks and rocky debris to microscopic dust particles. Though the rings appear solid from a distance, they're composed of countless particles, each tracing its own orbit around the host planet. These particles create intricate and shifting patterns within the rings, affected by the gravitational forces exerted by the planet, its moons, and even neighboring rings. But what forces initially conspired to form these rings? And what keeps them in such precisely balanced orbits over millions, even billions, of years? To understand the formation of planetary rings, scientists have proposed several theories. One of the leading ideas is that rings could be the remnants of a moon or other large object that strayed too close to its host planet and was torn apart by gravitational forces. Known as the Roche limit, this threshold marks the distance within which an object held together by self-gravity will disintegrate due to the planet's tidal forces overpowering its structural integrity. If a moon or asteroid ventures within this critical distance, the planet's gravitational pull can shred it into fragments, which then continue to orbit as a ring. This theory, while compelling, does not account for all rings, suggesting there may be multiple mechanisms at play. Another theory posits that some planetary rings might be the remnants of the primordial disk of dust and gas that surrounded young planets during their formation. According to this idea, certain particles from this disk may have remained in orbit around the planet, never coalescing into moons or larger bodies due to various gravitational and collisional factors. Over time, these particles would have organized into rings, with their structures shaped by the gravitational forces of the planet and any nearby moons. The presence of ring systems around gas giants, which are thought to have formed relatively early in the history of the solar system, gives some support to this theory. However, the complexities of ring formation challenge scientists to consider an array of possibilities. Intriguingly, recent discoveries reveal that ring systems may be more dynamic than previously believed. Far from static bands of debris, planetary rings are subject to constant change. Small collisions between particles can alter their orbits, causing them to spread out or cluster together. Solar radiation and magnetic fields can also affect the particles within the rings, leading to gradual drift or subtle changes in structure. And the gravitational influence of moons, often called shepherd moons, can sculpt rings into distinct shapes, creating gaps or lanes within the rings. These moons exert their pull on the particles, confining them to specific regions or even generating spiral waves within the ring, which gives rise to the breathtaking patterns observed in Saturn's rings. Saturn's rings, the most studied and striking of all, are not only visually captivating but scientifically invaluable. Recent data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided unprecedented insights into their composition and structure. Cassini revealed that Saturn's rings are primarily composed of water ice, with traces of rock and other materials, and range in size from fine dust-like particles to massive boulders. Cassini's observations also suggest that Saturn's rings are relatively young, perhaps only 100 to 200 million years old, a mere blink in the lifespan of the solar system. This youth raises new questions about how long rings can persist, and whether we are witnessing them in a temporary phase. Beyond the gas giants, planetary rings raise further mysteries when considering the possibility of ring systems around exoplanets. Given the sheer number of exoplanets discovered in recent years, scientists are beginning to speculate about the potential for rings around some of these distant worlds. Observations from Earth and space-based telescopes have suggested ring-like structures around certain exoplanets, though direct confirmation remains elusive. Nevertheless, the study of these potential rings could one day shed light on the broader cosmic conditions required for ring formation, helping us to understand if our solar system's ring planets are rare or common in the galaxy. One of the key factors influencing the formation and longevity of rings is the presence of moons. In cases where rings exist around planets without moons, such as Uranus, scientists are left to wonder how these rings maintain their structure and why they haven't dissipated over time. In contrast, Saturn's system of moons, each with its unique gravitational influence, appears to play a vital role in maintaining and shaping its rings. This dynamic between moons and rings hints at a delicate balance, the gravitational tug-of-war among particles, moons, and the planet itself creates a kind of cosmic choreography that holds the rings in place. One of the latest breakthroughs in ring science comes from studying the faint, ephemeral rings around Jupiter and Neptune. Unlike Saturn's bright and dense rings, the rings of these two gas giants are thin and sparse, barely visible even with powerful telescopes. These rings are thought to be composed mainly of dust, likely generated by meteor impacts on nearby moons that send particles into orbit around the planet. The transient nature of these rings, which are constantly replenished by new dust from impacts, suggests that some ring systems may not last indefinitely. Instead, they may be the result of ongoing processes that continually regenerate the ring material, challenging the notion that rings are always enduring features. As scientists continue to study the composition, dynamics, and formation of rings, they are also exploring why certain planets lack rings entirely. For example, Mars and Earth are notably devoid of ring systems, despite their relatively large masses and close proximity to the Sun. The absence of rings around these planets could be due to a variety of factors, including the gravitational influence of their moons, the stability of their orbits, or simply the lack of material within the Roche limit. However, there remains an open question as to whether Earth or Mars might have had rings in the distant past or could potentially develop them in the future under specific circumstances. The question of why some planets have rings while others do not extends beyond our solar system. As astronomers detect more exoplanets and investigate their potential characteristics, the prospect of finding ringed worlds outside our solar system becomes increasingly tantalizing. Rings around exoplanets could offer clues about the conditions under which these planets formed and evolved, providing a cosmic window into the processes shaping planetary systems beyond our own. In recent years, advancements in computer simulations have allowed scientists to model ring dynamics with unprecedented precision. These simulations, which account for factors like particle collisions, gravitational interactions, and solar radiation, offer a virtual laboratory for testing theories about ring formation and evolution. Through these models, researchers can observe how particles within a ring behave over time, gaining insights into the factors that contribute to ring stability or dissipation. Moreover, simulations can help scientists predict what a hypothetical ring system might look like around an exoplanet, or a planet like Earth, revealing the potential for rings to emerge under various cosmic scenarios. The study of planetary rings is a testament to humanity's unending curiosity about the cosmos. By probing these formations, scientists not only expand our understanding of the planets themselves but also the broader principles governing the universe. Rings reveal the hidden forces shaping planetary systems, the delicate balance between gravity and motion, and the fine line between order and chaos. Each ring system, whether massive like Saturn's or faint like Jupiter's, embodies the intricate and dynamic nature of the cosmos. As research continues, planetary rings may ultimately provide answers to some of the oldest questions about our solar system's formation and evolution. They may offer clues about the materials present in the early solar system, the conditions that favor ring formation, and the interplay between planets and their moons. And perhaps, as we look to the future, the study of rings around exoplanets will open new frontiers in our quest to understand the universe, hinting at the hidden beauty that exists in worlds far beyond our reach. The story of planetary rings is far from complete, with each new discovery adding layers of complexity to our understanding. One of the most fascinating aspects of ring science is the delicate balance of forces that maintains the stability of these rings. In particular, the interplay between gravity and angular momentum creates a finely tuned system, where each particle is caught in a constant tug-of-war between the gravitational pull of the host planet and its own inertia as it orbits. This dynamic equilibrium ensures that particles stay confined within the ring structure, rather than spiraling into the planet or dispersing into space. In the case of Saturn, we see this balancing act on a grand scale. Saturn's rings are divided into several distinct sections, each with its own unique properties. These divisions, such as the A, B, and C rings, are not arbitrary. They are shaped by the gravitational influence of Saturn's many moons, as well as the resonant orbits of particles within the rings themselves. For example, Saturn's moon Mimas, located just outside the rings, exerts a gravitational resonance that helps maintain a prominent gap known as the Cassini division. This gap is not merely an absence of particles but a region shaped by complex gravitational interactions, where particles are subtly nudged out of certain orbits, creating a striking division that gives Saturn's rings their iconic appearance. The study of these gaps and divisions has led scientists to a deeper understanding of how moons and other celestial bodies influence ring dynamics. In addition to the Cassini division, Saturn's rings contain a variety of other gaps, some created by smaller moons called shepherd moons. These moons, often no larger than a few kilometers across, orbit within or just beyond the edges of the rings, exerting a gravitational force that corrals particles into specific regions. The result is a sculpted ring system, where gaps and lanes are carved out, forming the intricate structure we observe. Shepherd moons like Pan and Daphnis play a critical role in maintaining this structure, demonstrating that even small bodies can have a profound impact on the architecture of a ring system. Beyond the mechanics of ring formation, scientists are also deeply interested in the composition of ring particles. Saturn's rings, for instance, are primarily composed of water ice, giving them their bright, reflective appearance. But this icy composition is not universal. The rings of Uranus and Neptune, for example, are darker and less reflective, suggesting a different composition, possibly including a higher proportion of rocky material or organic compounds. The presence of such diverse compositions hints at the varied origins of ring systems across the solar system. It raises questions about whether rings are remnants of planetary formation, shattered moons, or captured interplanetary debris. Understanding the age of these rings also remains a tantalizing challenge. While Saturn's rings are thought to be relatively young, possibly less than 200 million years old, other ring systems may be far older. This discrepancy in age across ring systems has led scientists to consider a range of factors that could influence ring longevity. For instance, gravitational interactions with nearby moons may either stabilize or destabilize rings over time. Additionally, the influx of interplanetary dust and meteoroids can erode ring particles, gradually reducing the overall mass of the ring system. Such processes may lead to the eventual dissipation of rings, transforming them from prominent features into faint halos, or even causing them to disappear entirely. The potential for ring formation around planets outside our solar system, exoplanets, adds yet another layer to this fascinating puzzle. Though direct observation of exoplanetary rings remains challenging with current technology, scientists have detected hints of ring-like structures around distant planets. Some of these rings, if confirmed, could dwarf even Saturns in size and scale. The study of exoplanetary rings could reveal new insights into planetary formation, as well as the environmental conditions that favor the development of rings. By examining these rings, astronomers hope to learn more about the diversity of planetary systems and the evolutionary pathways that lead to such varied outcomes. One particularly intriguing candidate for an exoplanetary ring system is the planet J1407b, which orbits a star about 420 light-years from Earth. Observations of this distant planet suggest it could possess a massive ring system with a diameter far exceeding that of Saturn's rings. If confirmed, the rings of J1407b could contain up to 100 times the mass of Earth's moon, forming a structure so vast that it would be visible to the naked eye from Earth if placed in our own solar system. The existence of such a ring system challenges our assumptions about ring formation, suggesting that under certain conditions, rings may grow to extraordinary proportions, potentially serving as a source of moons over time. The process by which rings give rise to moons, known as moonlet formation, is another area of active research. Some scientists believe that the particles within a ring system can coalesce under the right conditions, gradually forming larger bodies that eventually become moons. This process, similar to how planets are thought to form from protoplanetary disks, could explain the presence of small, irregular moons near the edges of certain rings. These moonlets, in turn, could influence the structure and stability of the rings, creating a feedback loop in which rings and moons shape one another over time. Jupiter's faint ring system, while less visually striking than Saturn's, provides valuable clues about the origins of rings around gas giants. Unlike Saturn's icy rings, Jupiter's rings are composed mainly of dust, likely generated by meteoroid impacts on its small inner moons, such as Métis and Adrastea. When meteoroids collide with these moons, they send dust and debris into orbit, forming a thin, faint ring around the planet. This process, while less dramatic than the formation of Saturn's rings, demonstrates that rings can arise from various mechanisms, each producing rings with distinct characteristics and lifespans. The study of Neptune's rings has also yielded surprising insights. Neptune's rings are relatively narrow and incomplete, consisting of clumpy arcs rather than continuous bands. This fragmented structure remains a mystery, as scientists are still working to understand why Neptune's rings have formed in such a unique pattern. One theory suggests that gravitational interactions with Neptune's moon Galatea, which orbits near the rings, may be responsible for the arcs. These gravitational forces could trap particles within specific regions, preventing the rings from spreading out into a continuous band. Neptune's rings challenge our understanding of ring stability and highlight the diversity of ring systems within our solar system. In addition to rings around planets, astronomers have also discovered ring systems around smaller bodies, such as asteroids and dwarf planets. The discovery of rings around the asteroid Chariklo, a centaur located between the orbits of Jupiter and Neptune, was an unexpected finding that broadened the scope of ring science. Chariklo's rings, composed of narrow bands of dust and ice, demonstrate that even small, irregular objects can host ring systems. This discovery has led scientists to reconsider the conditions under which rings can form, suggesting that rings might be more common in the solar system than previously thought. Another fascinating discovery was the detection of rings around the dwarf planet Haumea, located in the Kuiper belt beyond Neptune. Haumea's ring, coupled with its rapid rotation, adds a unique twist to our understanding of ring formation. Scientists believe that Haumea's rapid spin may play a role in sustaining its ring, possibly by generating a gravitational field strong enough to retain ring particles despite the dwarf planet's relatively small mass. The existence of rings around Haumea suggests that certain rotational and orbital characteristics could promote ring formation, even around small bodies far from the Sun. As we continue to study ring systems across the solar system, the role of observational technology becomes increasingly important. Instruments like the Hubble Space Telescope and the James Webb Space Telescope, along with specialized ground-based observatories, enable scientists to probe ring systems with remarkable precision. These tools allow astronomers to observe the structure, composition, and behavior of ring particles in ways that were previously impossible, shedding light on phenomena like ring wave patterns, particle collisions, and the effects of radiation pressure. Each new observation brings us closer to understanding the intricate details of ring dynamics and the forces that sustain these enigmatic structures. Looking ahead, future missions to the outer planets could provide even more detailed data on planetary rings. A return mission to Saturn, for example, could explore the rings in greater depth, examining the composition and structure of particles on a microscopic level. Such a mission could also investigate the potential presence of organic compounds within the rings, which could offer clues about the origins of life and the chemical processes occurring in the outer solar system. Similar missions to Uranus and Neptune, where ring systems remain largely unexplored, could reveal entirely new phenomena, potentially revolutionizing our understanding of ring dynamics. Ultimately, the study of planetary rings is about more than just understanding these beautiful structures. It's about uncovering the fundamental processes that shape the cosmos. Rings offer a unique glimpse into the physics of planetary systems, the forces that govern orbital dynamics, and the delicate balance between order and chaos. Each ring system, from the dense bands of Saturn to the faint dust of Jupiter, tells a story about the planet it surrounds, the moons that influence it, and the cosmic events that brought it into existence. As we continue to unlock the secrets of planetary rings, we not only deepen our knowledge of our own solar system but also prepare ourselves for the exploration of distant worlds, where ring giants may orbit unknown stars in patterns and formations we have yet to imagine. Exploring the science of planetary rings also raises profound questions about the broader universe and its mysteries. Each ring system we study is, in some sense, a small-scale laboratory for testing theories about disk formation and the dynamic interactions within them. These questions extend beyond our solar system and into the realm of galaxies and star systems, where similar processes shape entire galaxies. One concept that links the science of planetary rings with the larger cosmos is the protoplanetary disk theory. Protoplanetary disks are massive clouds of gas and dust surrounding young stars, from which planets form over millions of years. This process is remarkably similar to how rings may eventually give birth to moons. By studying the small-scale interactions within planetary rings, scientists gain insight into the processes that govern the formation of entire solar systems. For example, understanding how particles within Saturn's rings coalesce to form denser clumps or small moonlets provides a model for how planets might form around stars. An interesting aspect of ring dynamics is how tiny forces and influences can have major impacts on ring stability and structure. For instance, electromagnetic forces and interactions with the solar wind can affect the particles within a ring, especially in the case of Saturn, where the planet's strong magnetic field interacts with its rings. The particles in the rings are not merely floating through empty space. They are bombarded by solar radiation, cosmic rays, and magnetic fields. These forces can strip particles of electrons, creating electrically charged particles that interact in complex ways, sometimes pushing or pulling them out of their usual orbits. The phenomenon of spokes in Saturn's rings provides a perfect example of these kinds of interactions. Observed as mysterious, fleeting dark features within the rings, spokes are thought to be caused by tiny electrically charged particles lifted slightly above the ring plane by interactions with Saturn's magnetic field. Spokes come and go, appearing and disappearing as the conditions within the rings change, demonstrating the ever-evolving nature of these systems. The Cassini spacecraft provided detailed observations of these spokes, allowing scientists to understand them better, yet they remain a reminder of the complexity of ring dynamics. Another mystery lies in the ring particle sizes. Saturn's rings, for example, contain particles ranging from tiny dust grains to boulder-sized chunks. The range in size leads to fascinating behaviors within the rings, such as particle collisions that transfer energy and momentum. These collisions can cause particles to aggregate, forming larger clumps or break apart into smaller fragments, depending on their speed and the angle of impact. The constant cycle of collisions, aggregation, and fragmentation is what gives rings their unique structure, as particles naturally find orbits that minimize the likelihood of collisions, thus creating a stable system. Dust also plays an intriguing role in the evolution of planetary rings. While much of the material in Saturn's rings is icy, it accumulates interplanetary dust over time, leading to gradual changes in color and composition. This accumulation process has been observed by the Cassini spacecraft, which detected darker, reddish hues in certain parts of Saturn's rings, likely the result of dust accumulation over millions of years. These findings suggest that rings are not static but change and evolve over time, influenced by both internal processes, like particle collisions, and external factors, such as dust accumulation. While the primary components of planetary rings may differ from planet to planet, it is the interaction between the rings and their respective environments that gives each ring system its distinct characteristics. For instance, Uranus's rings are narrow and dark, likely due to a combination of their rocky composition and the influence of Uranus's extreme tilt. This axial tilt, nearly perpendicular to the planet's orbit, means that Uranus's rings experience seasonal variations in sunlight exposure, potentially affecting their structure and visibility. In contrast, Neptune's rings contain prominent arcs, regions of concentrated material, possibly maintained by the gravitational effects of Neptune's moons. Each of these systems reflects a unique balance between the forces acting upon it, leading to an incredible diversity of ring structures. The transitory nature of rings is another fascinating aspect. Scientists believe that rings may be ephemeral in the grand timeline of a planet's life, with some ring systems forming and dissipating over tens or hundreds of millions of years. For instance, Saturn's rings may be relatively young, potentially formed by the breakup of a comet or moon within the last 200 million years. Over time, as particles collide and are drawn into the planet by gravity or radiated away, the rings may thin out and disappear. This transient nature suggests that ring systems could be a common but temporary feature, possibly appearing at different stages in a planet's history. This leads to an intriguing hypothesis. Could some of the planets we observe today have hosted rings in the past, which have since dissipated? Alternatively, could planets that currently lack visible rings form them in the future, perhaps after a collision event? The idea that ring systems might come and go adds an exciting dynamic to planetary science, suggesting that the life cycle of a ring could be as complex and variable as the life cycle of a moon or a planet. Recent observations have also uncovered the possibility that ring systems may exist around young stars and even some white dwarfs. In these cases, the rings are composed of debris from planetary bodies that were either destroyed during the star's formation or disintegrated by the intense gravitational forces around the white dwarf. This unexpected discovery extends the presence of rings beyond planets and small bodies, indicating that rings could be a common cosmic feature even in stellar environments. The presence of rings around white dwarfs, in particular, suggests that ring systems may persist long after the original planets have been destroyed, serving as a kind of memorial to once thriving planetary systems. On the observational front, advancements in space telescopes and imaging technology are bringing planetary rings into sharper focus than ever before. Instruments like the James Webb Space Telescope are expected to provide unprecedented detail of ring systems, both within our solar system and around distant exoplanets. The ability to observe rings in infrared and other wavelengths will allow scientists to study their composition, temperature, and particle distribution with greater precision. This technological progress is vital, as the more we can see and measure, the better we can understand the underlying physics of these beautiful and complex systems. One particularly tantalizing mystery lies in the possible detection of rings around rogue planets. Planets that do not orbit a star but instead drift freely through the galaxy. These rogue planets may have been ejected from their parent star systems due to gravitational interactions or collisions. If such planets could sustain ring systems, it would imply that rings are not only bound to star-orbiting planets, but could also form and persist in the isolated voids of interstellar space. Detecting rings around rogue planets would be challenging, as they do not emit their own light and are extremely difficult to observe. However, such a discovery would profoundly expand our understanding of the environments where rings can exist. Another area of inquiry is the potential impact of rings on planetary climates and atmospheres. For example, Saturn's rings are thought to have a subtle effect on the planet's upper atmosphere. As particles from the rings gradually drift inward due to gravitational interactions, they enter the atmosphere, where they create a faint glow known as ring rain. This process delivers water and other materials to the planet, potentially influencing its atmospheric composition over long timescales. The extent to which this ring rain affects Saturn's climate is still being studied, but it raises intriguing questions about how rings might influence the atmospheres of gas giants in other solar systems. As scientists continue to explore these possibilities, planetary rings reveal themselves as dynamic, ever-changing systems that defy simple explanations. Each ring system embodies a delicate balance of forces, a snapshot of cosmic processes at work on a grand scale. And while the visible rings around planets like Saturn may one day fade, their impact on our understanding of celestial mechanics, planetary formation, and the mysteries of space will endure. In many ways, planetary rings are cosmic tapestries, woven by the invisible hands of gravity, magnetism, and time, each telling a story about the planets they orbit and the forces that shape them. In the ongoing quest to understand planetary rings, scientists frequently encounter phenomena that challenge established theories. Rings are not just passive accumulations of dust and ice. They are shaped and reshaped by a complex array of forces that vary from one planet to the next. The gravitational pull of nearby moons, the influence of a planet's magnetosphere, and even interplanetary forces can mold rings into intricate patterns. This interplay of forces creates features like the shepherd moons that guide and maintain ring boundaries, preventing particles from dispersing and helping to create well-defined edges within the rings. Shepherd moons are a fascinating aspect of ring systems, especially around Saturn, where moons like Prometheus and Pandora play critical roles in shaping the F-ring. As these small moons orbit Saturn, they tug on ring particles, herding them into tight formations and preventing them from spreading out. This herding effect is not only responsible for the F-ring's sharp boundaries but also for its complex structure, which includes strands and kinks that would otherwise not exist. Observing these interactions helps scientists understand the delicate gravitational interplay between moons and ring particles, offering insights into orbital mechanics that extend beyond planetary rings. Shepherd moons can also create wave patterns within rings, such as those observed in the A and B rings of Saturn. These waves resemble ripples on the surface of a pond, caused by the gravitational influence of nearby moons. When a shepherd moon passes close to a ring, its gravity pulls on ring particles, creating a density wave that propagates through the ring. These waves allow scientists to probe the physical properties of the rings, as the way waves move and dissipate can reveal information about particle size, density, and the composition of the ring material. By analyzing these wave patterns, researchers gain a unique perspective on the microscopic structure of ring particles. The gravitational effects that shape planetary rings can even give rise to ring gaps, distinct gaps or clearings within the rings where few particles are present. One of the most famous examples is the Cassini division, a dark gap between Saturn's A and B rings. The Cassini division is caused by a phenomenon known as a resonance, where particles within the gap have orbital periods that are simple ratios of the orbital period of one of Saturn's moons. This resonance destabilizes the orbits of particles, effectively clearing out the region and creating a distinct gap within the ring system. Resonances are not unique to Saturn. They also play roles in the rings of other planets, and even in the asteroid belt between Mars and Jupiter. Beyond their aesthetic and scientific appeal, planetary rings could hold clues about the early conditions of our solar system. The processes that govern ring formation, maintenance, and destruction may parallel the processes that shaped the primordial solar nebula from which the planets themselves formed. In a sense, ring systems serve as a microcosm of solar system formation, allowing scientists to test models of disk dynamics on a smaller scale. By examining how particles within a ring system interact, scientists can simulate how protoplanetary disks coalesce to form planets, stars, and other celestial bodies. One particularly captivating idea is that studying ring systems could help astronomers understand exoplanetary systems. Since our own solar system appears to have only limited examples of rings beyond the gas giants, researchers are curious whether other star systems might host planets with rings, or even planets with rings more massive and complex than Saturn's. As telescopes and observation technology improve, the possibility of detecting rings around exoplanets grows more likely. In fact, astronomers have already detected hints of massive ring systems around distant planets. For example, one exoplanet known as J1407b may host an extensive ring system much larger than Saturn's, with rings that could potentially stretch across a space hundreds of times wider than Saturn's rings. Detecting rings around exoplanets could also aid in the discovery of habitable zones and Earth-like planets. When a ringed exoplanet passes in front of its star, the ring can create a unique light signature, causing the star's light to dim in a specific pattern. This phenomenon, known as a transit, is one of the primary methods astronomers use to detect exoplanets. Rings complicate this process, as they can distort the light curve in ways that hint at their presence. By analyzing the transit patterns caused by rings, astronomers may be able to infer the size, density, and composition of these rings, as well as the properties of the planet they orbit. This indirect observation method could unlock new insights into the structure and diversity of planetary systems far beyond our own. The impact of rings on planetary science goes beyond mere observation. It challenges scientists to rethink traditional theories of planet formation and stability. For instance, if rings are found to be common around exoplanets, it may suggest that ring formation is a natural byproduct of planetary evolution. Alternatively, if rings are rare or unique to certain types of planets, it could imply that specific conditions are necessary for rings to form and persist. These discoveries could reshape our understanding of planet formation and the processes that lead to the development of diverse planetary systems. Back within our solar system, planetary rings also offer a glimpse into the potential for future space exploration and resource utilization. Some scientists have speculated that rings, particularly those composed of water ice, could serve as valuable resources for future missions. Saturn's rings, for instance, contain vast amounts of water ice, which could theoretically be harvested for fuel or drinking water in a space station or outpost. However, accessing and mining the rings presents significant challenges, as the gravitational and electromagnetic forces within the rings would make it difficult to establish stable operations. Nonetheless, the potential of rings as a resource could become an intriguing area of research as space exploration advances. The rings of gas giants may even hold clues to the habitability of their moons. For instance, Jupiter's rings interact with its moons, particularly Io, which is the most volcanically active body in the solar system. The particles ejected from Io's volcanoes interact with Jupiter's magnetic field, contributing to the formation of its faint ring system. This interaction creates a dynamic and complex environment where particles move between the planet and its moons. Such interactions could potentially influence the habitability of other moons by affecting their atmospheres or by transferring essential compounds, like water, between celestial bodies. Another thought-provoking theory about planetary rings is their potential role as planetary shields. Rings could act as a protective barrier, absorbing or deflecting incoming meteoroids and space debris that might otherwise impact the planet or its moons. While the rings themselves might experience constant bombardment, they could effectively reduce the frequency of collisions with the planet. This shielding effect could have implications for the development of life on moons orbiting within or near a ring system, as it may reduce the likelihood of catastrophic impacts. Beyond the tangible science of planetary rings lies a more abstract fascination. Rings serve as a reminder of the sheer beauty and complexity of the cosmos. The existence of rings challenges us to expand our view of what planets can be and what solar systems can look like. Rings bring an added layer of diversity to our universe, showing us that even in the void of space, intricate structures can form, evolve, and captivate our imaginations. The ever-changing nature of rings, the interplay of forces within them, and the fleeting lifespan they may have are all testaments to the universe's creativity and dynamism. As we continue to learn more about the rings within our solar system, we are constantly reminded of how much we have yet to discover. The study of planetary rings is not just about understanding a specific feature of certain planets. It's about uncovering the principles that govern all matter, from dust particles in a ring to the stars and galaxies that make up our universe. Planetary rings are just one example of the cosmos's ability to surprise and intrigue us, offering a glimpse into the physical laws that bind everything together. The rings of Saturn, Uranus, Jupiter, and Neptune stand as magnificent monuments to the forces of nature. They embody both the elegance and the ferocity of gravitational dynamics, the subtle influence of magnetism, and the resilience of particles in the face of constant change. These rings tell a story, not just of the planets they encircle, but of the universe as a whole, its creativity, its vastness, and its boundless complexity. With every new observation, whether from a spacecraft like Cassini or a telescope peering into the depths of space, we draw closer to unraveling the mysteries of planetary rings. The knowledge we gain does not only enrich our understanding of these beautiful structures but also deepens our appreciation for the cosmos and our place within it. Planetary rings are among the universe's most remarkable spectacles, and they continue to invite us to explore, to wonder, and to reach for understanding in a vast and mysterious universe. As we dive deeper into the mysteries of planetary rings, we come to realize that they are far more than simple adornments around planets. They are dynamic systems that play a significant role in the lives of their host planets, and even in the evolution of the planetary systems around them. For example, the gravitational influences of a planet's rings can affect the orbital paths of its moons, sometimes even dictating the long-term stability of the entire planetary system. These intricate relationships between rings, moons, and planets offer a unique perspective on how celestial bodies interact in complex and sometimes unexpected ways. Take Saturn's moons as an example. Some of them are closely linked to the rings and even contribute to their structure. Enceladus, one of Saturn's most intriguing moons, ejects plumes of water vapor and icy particles from its surface, which are thought to replenish Saturn's E-ring. This exchange between a moon and its planet's ring system highlights a fascinating aspect of ring science. Rings are not isolated features, but rather interconnected with their surrounding environment. This interaction raises questions about the potential for similar processes occurring around moons and planets in other star systems, where ring planets might host moons with their own active geologies. The concept of replenishment is vital to understanding ring longevity. Rings are constantly losing particles due to various forces, such as solar radiation, collisions with micrometeoroids, and the gravitational pulls of nearby bodies. If rings lose material at a faster rate than they gain, they would eventually dissipate. However, in systems like Saturn's, the interactions with moons like Enceladus add new particles back into the ring, effectively extending its lifespan. This balance between loss and gain hints at the delicate processes that sustain ring systems over millions of years and reveals how rings might persist around certain planets for far longer than previously expected. Meanwhile, the physical structure of planetary rings offers insight into the composition and formation history of the rings themselves. Saturn's rings, for instance, are primarily made up of water ice, with particles ranging from tiny ice grains to massive boulders. This composition suggests that the rings might have originated from icy moons or comets that came too close to Saturn and were torn apart by tidal forces. In contrast, the rings of Uranus and Neptune contain darker, less reflective material, hinting that they may have originated from different sources, such as ancient moons composed of carbon-rich compounds. This diversity in ring composition is key to understanding why rings around different planets vary so dramatically and why some planets, like Mars and Venus, lack substantial ring systems altogether. Understanding why certain planets have prominent rings while others do not leads us to explore the concept of the Roche limit. This is the distance within which a celestial body, held together only by its own gravity, will be torn apart by the tidal forces of a larger body. For example, if a moon or comet ventures too close to a planet and crosses within its Roche limit, the planet's gravitational forces will overcome the object's own gravity, causing it to disintegrate and form a ring. This concept explains why gas giants, with their powerful gravitational fields, are more likely to host rings than smaller, less massive planets. In the case of gas giants, their immense gravity creates a large Roche limit that can capture and disintegrate objects, leading to ring formation. On the other hand, planets like Mars and Earth do not have rings, possibly due to their smaller Roche limits and weaker gravitational fields. Objects that come close enough to these planets either escape their gravitational influence, or crash onto the planet's surface instead of breaking apart into a ring system. This difference in gravitational pull and tidal forces underscores the role that a planet's size and mass play in determining whether it will develop a ring system. Additionally, environmental factors such as atmospheric drag and solar radiation pressure can quickly destabilize ring particles around smaller planets, preventing the formation of stable rings. Interestingly, planetary rings also serve as records of the cosmic environment in which they formed. Saturn's rings, for instance, might hold clues to the conditions present in the outer solar system during the planet's formation. By studying the isotopic composition of ice particles within Saturn's rings, scientists can glean information about the chemical environment of the early solar system. These particles act as fossils, preserving the conditions under which they were formed. In this way, rings offer a unique window into the past, enabling researchers to understand not just the history of a specific planet, but the history of the solar system as a whole. More recently, discoveries regarding the age of Saturn's rings have sparked intense debate within the scientific community. Initially, scientists believed that Saturn's rings formed alongside the planet itself, making them over 4 billion years old. However, recent findings from the Cassini spacecraft suggest that Saturn's rings may be significantly younger, perhaps only a few 100 million years old. The relatively young age of the rings raises new questions about how and when they formed, as well as what cataclysmic events might have led to their creation. One hypothesis suggests that a moon or comet was shattered in a collision with Saturn or one of its moons, producing debris that eventually coalesced into the rings we observe today. The debate over the age of Saturn's rings underscores a broader mystery about planetary rings in general. Are rings temporary phenomena, appearing and disappearing over the lifespan of a planetary system, or are they enduring features that persist for billions of years? This question touches on the heart of planetary ring science, as it challenges scientists to consider whether rings are an essential, long-lasting feature of certain planets, or simply transient structures that arise under specific conditions. Resolving this mystery will require further data from future space missions and possibly even close-up studies of rings around exoplanets. Another captivating discovery in recent years concerns the seasonal changes observed within Saturn's rings. As Saturn orbits the Sun over a 29-year period, its rings experience varying levels of solar radiation, which can affect their brightness and structure. When Saturn's rings are tilted edge-on to the Sun, they receive less sunlight, causing the icy particles to appear darker. In contrast, when the rings are fully exposed to sunlight, they brighten, revealing more detail. Observing these seasonal variations provides scientists with a unique opportunity to study how external forces, like solar radiation, influence ring systems and to understand how rings may evolve over time. Magnetic fields also play a significant role in shaping ring dynamics, especially around planets like Jupiter and Saturn, which possess powerful magnetospheres. These magnetic fields interact with the charged particles within the rings, creating electromagnetic forces that can alter the movement of particles, causing them to spiral inward or outward. This phenomenon, known as magnetic drag, can even lead to the formation of faint ring structures, as charged particles follow magnetic field lines rather than purely gravitational paths. Studying these magnetic interactions offers insights into the electrical and magnetic properties of ring particles and helps scientists understand how magnetic forces influence ring stability and shape. Beyond their scientific significance, planetary rings inspire a sense of wonder and beauty. The elegance of Saturn's rings, with their delicate structure and shimmering ice particles, has captivated human imagination for centuries. Rings remind us of the complex and ordered structures that can emerge in the vastness of space, driven by natural forces that operate on both grand and minute scales. They serve as cosmic art, shaped by gravity and motion, with every particle in constant motion, bound together by invisible forces. The study of planetary rings continues to evolve, driven by both new technologies and new theories. Future missions, such as those that might explore the outer planets in greater detail, could provide fresh insights into the composition, structure, and evolution of these fascinating systems. Perhaps one day, scientists will even be able to examine rings around exoplanets directly, revealing whether these structures are a common feature in the galaxy or a rare phenomenon unique to our solar system. As we explore the final frontier, planetary rings stand as reminders of the beauty and mystery that lie beyond our own world. They beckon us to keep searching, to keep asking questions, and to keep reaching for a deeper understanding of the universe. In studying rings, we not only learn about distant worlds but also about the forces that shape our own planet, and, ultimately, our place in the cosmos. In the grand tapestry of the universe, rings are among the most intricate threads, woven through the lives of planets, moons, and stars, embodying the unity and diversity of the cosmos. The mysteries of planetary rings stretch even further as we consider the possibility of ringed exoplanets, planets outside our solar system that might possess their own rings. Detecting these rings is incredibly challenging given the limitations of current telescope technology and the vast distances involved. However, astronomers have made some promising observations, hinting that ringed exoplanets might indeed exist. One particularly intriguing case is that of J1407b, a possible exoplanet with an enormous ring system, discovered through the dimming patterns it creates when it passes in front of its star. The ring system of J1407b is thought to be more than 200 times larger than that of Saturn, which, if confirmed, would make it the largest ring system ever observed. This potential discovery opens the door to a new area of planetary science. If exoplanets can indeed have rings, it raises numerous questions about how these rings might form and evolve in different star systems. For instance, would a ring system in a binary star system experience forces that break it apart? Or could it stabilize in a unique way under the gravitational influences of two stars? Understanding ring dynamics in these alien environments could also reveal new processes that we haven't observed in our own solar system. Exoplanet rings could vary dramatically in their composition as well. While we know that Saturn's rings are primarily made up of water ice, rings around planets orbiting stars that are closer to the galactic center, where metallic elements are more abundant, could contain dust, silicate, or even metal-rich particles. This compositional diversity could lead to rings that look completely different from anything we have seen, with colors and textures influenced by entirely different chemical elements. These differences would not only make exoplanetary rings fascinating to study but also challenge our understanding of how materials are distributed and recycled in the galaxy. Exploring the potential for life within ring systems introduces yet another fascinating dimension. Though rings themselves are not likely to support life, they might influence the habitability of moons orbiting within or near them. For instance, a ring system can affect the temperature and radiation levels around a moon, possibly providing a stable environment that shields against harmful cosmic radiation. In the case of Saturn's moon Enceladus, scientists have speculated that interactions with Saturn's E-ring may affect the moon's surface temperature and influence the chemical makeup of its icy shell, possibly contributing to the conditions needed to sustain microbial life. Additionally, rings around exoplanets could potentially serve as indicators of past or ongoing planetary formation processes. Just as we've observed that rings can form from the breakup of moons or comets, the existence of rings around exoplanets could hint at recent cosmic events, such as the capture or destruction of a moon. This process might be a natural part of planetary evolution, with rings forming and dissipating over geological timescales as moons are captured or disintegrate. The study of these rings could offer a rare glimpse into the life cycle of planets and moons, helping scientists piece together how planetary systems evolve and mature over time. Gravitational forces within ring systems create astonishing phenomena, including the formation of shepherd moons. These are small moons that orbit within or along the edges of rings, exerting gravitational influence that helps maintain the ring structure. Saturn's shepherd moons, such as Prometheus and Pandora, play a critical role in sculpting the edges of the F-ring, preventing particles from drifting too far. The interplay between these moons and ring particles creates patterns and waves within the rings, adding yet another layer of complexity to their dynamics. These interactions are sometimes referred to as wave propagation, where the shepherd moon's gravitational pull creates spiral density waves that travel through the rings. Shepherd moons act like cosmic custodians, keeping the ring particles in line and preventing them from dispersing. The existence of shepherd moons also raises questions about the potential for similar moons around ringed exoplanets, which could maintain and shape those distant ring systems in similar ways. Understanding these moons and their effects could shed light on how stable ring systems might be in the long term and whether they could survive for billions of years or are destined to be temporary features. In some cases, rings can form gaps, or voids, where no particles are present. One famous example is the Cassini division in Saturn's rings, a large gap between the A and B rings created by gravitational resonance with Saturn's moon Nemesis. Such gaps are important clues for scientists because they reveal where gravitational forces are disrupting the stability of ring particles. Studying these voids helps scientists understand how moons and ring particles interact across large distances and how the gravitational forces between them create and maintain these intricate patterns. These gaps and structures are not unique to Saturn. We see similar patterns in the rings of other gas giants. For instance, Uranus has several narrow rings with dark gaps, and Neptune's rings include arcs, or clumps, which are denser regions within the rings. These irregular structures reveal that planetary rings are not static but are instead vibrant, constantly evolving systems shaped by a variety of forces, including gravity, collisions, and even magnetic fields. Rings can also experience mysterious processes known as spokes. These are radial, spoke-like features observed in Saturn's rings, which were first detected by the Voyager spacecraft and later studied in detail by Cassini. These spokes appear and disappear, seemingly defying the stable, orderly movement of the rings. Scientists believe that the spokes may be caused by electromagnetic forces interacting with fine particles in the rings, temporarily lifting them above the ring plane. While the exact cause of these spokes is still unknown, their presence underscores the dynamic and sometimes unpredictable nature of ring systems. Further studies of ring dynamics have shown that ring particles are constantly colliding with each other, leading to a kind of self-regulating behavior within the ring. When two particles collide, they transfer energy and momentum, often leading to changes in their individual orbits. Over time, these collisions tend to smooth out differences in particle speed, creating a more uniform structure in which particles move in a coordinated manner. This process of collisional damping is another reason why rings can maintain their shape over long periods, even in the face of external forces that might otherwise disrupt them. In addition to gravitational interactions, the influence of sunlight plays a unique role in ring evolution. When sunlight strikes the particles within a ring, it creates what is known as radiation pressure. Although this force is relatively weak compared to gravity, it can have a cumulative effect on the smallest particles in the ring, slowly pushing them outward over time. This process, known as the Poynting-Robertson effect, gradually removes smaller particles from the rings, subtly altering the ring's composition and structure. The study of this effect reveals how even the faintest forces can shape the vast and delicate structures of rings. Ultimately, planetary rings continue to be some of the most captivating and complex structures in our solar system, and potentially beyond. They embody the delicate balance of forces that exist throughout the cosmos, from the gravitational tugs of nearby moons to the steady pressure of sunlight. The continued study of rings holds the promise of answering many questions, not only about their origins and structure but also about the fundamental forces that govern planetary systems. As humanity pushes forward with new missions to explore the outer reaches of our solar system and beyond, planetary rings remain a key area of interest. By studying these natural marvels, scientists gain insights not only into the formation of rings themselves but into the very nature of planets, moons, and the cosmic interactions that bind them. These discoveries enhance our understanding of the universe and remind us of the endless mysteries that await our exploration. Planetary rings, with their intricate beauty and scientific value, continue to capture our imagination and beckon us to venture further into the unknown. Looking forward, the exploration of planetary rings holds immense potential for future discoveries. While current spacecraft missions like Cassini and Voyager have vastly increased our understanding of ring dynamics, new technologies are set to take this exploration even further. With advances in telescope resolution, observational techniques, and space probe capabilities, scientists anticipate being able to study ring systems in unprecedented detail, possibly observing changes in real time. For instance, the upcoming James Webb Space Telescope, JWST, has already begun offering glimpses into distant exoplanets and could be pivotal in detecting ring systems around those worlds. Similarly, upcoming missions to the outer solar system may help scientists capture intricate details of the rings around Uranus and Neptune, providing a more complete understanding of these distant worlds. One of the most promising aspects of these future missions is the potential to unlock new insights into the chemical composition of rings. Although we know that Saturn's rings contain a high proportion of water ice, questions remain about the presence of organic compounds or complex molecules. Future missions equipped with advanced spectrometers could probe the rings in fine detail, helping to determine the precise makeup of the dust and ice particles. This exploration could reveal new insights into the materials that formed in the early solar system, as well as how they've been altered by radiation and other cosmic influences over billions of years. Another area of exploration will be understanding the interactions between rings and planetary magnetospheres, which is a magnetic region surrounding a planet. For planets like Saturn and Jupiter, the intense magnetic fields interact with ring particles, potentially creating electric currents and influencing the distribution of particles within the rings. This phenomenon is still not entirely understood, but future missions with instruments that can measure magnetic and electric fields directly could provide crucial data. Such information would help explain how these planetary magnetic fields shape and perhaps even sustain the ring systems over long periods. Moreover, scientists are intrigued by the potential for ring rain, a phenomenon in which particles from the rings gradually fall onto the planet below, influenced by magnetic fields and gravity. Saturn, in particular, is known to experience this ring rain, where charged particles are drawn along magnetic field lines and enter the planet's atmosphere. This process slowly drains material from the rings and may contribute to the gradual decay of the ring system over time. By studying this interaction more closely, researchers could better understand how long rings can endure and what factors might contribute to their eventual dissipation. The longevity of rings remains one of the great unknowns in planetary science. Saturn's rings, for example, are estimated to be around 100 million years old, which is relatively young in cosmic terms, especially when compared to the age of the solar system itself. This youth raises questions about whether ring systems are a transient phase that gas giants go through, rather than a permanent feature. If rings are indeed short-lived, it would imply that we are witnessing a relatively rare event in Saturn's lifespan, a unique cosmic phenomenon that might not exist forever. Future studies could determine if these structures are indeed ephemeral and what specific processes might lead to their eventual disappearance. The question of why some planets have rings while others do not is also a mystery that scientists continue to investigate. Our current theories suggest that rings require a delicate balance of forces to remain stable, which might explain why Earth, Venus, and Mars lack rings. Factors such as a planet's gravitational pull, the presence of moons, and the impact of cosmic collisions all play a role in determining whether a ring system can form and persist. In the case of gas giants, their larger mass and stronger gravitational fields make it easier for them to capture and maintain ring materials. But even within the category of gas giants, significant differences exist. Jupiter's rings, for instance, are thin and faint compared to Saturn's. Understanding these disparities could reveal insights into the conditions required for rings to form and survive. The rings of Jupiter, Saturn, Uranus, and Neptune offer valuable comparisons for scientists. While Saturn's rings are bright and easily visible, Jupiter's are much fainter, composed mostly of small, dark particles. Uranus and Neptune have similarly dark rings, which are thin and difficult to observe from Earth. These differences are thought to arise from variations in the size and composition of the particles within the rings, as well as from different processes affecting each planet. For example, Jupiter's rings are primarily made of fine dust particles created by meteoroid impacts on its moons, while Saturn's are composed of larger ice chunks that reflect more sunlight, making them more visible. Comparing the rings of different gas giants not only highlights their diversity, but also allows scientists to test various theories about ring formation and stability. The fact that these planets possess rings of such varied appearances and structures suggests that ring formation can occur through multiple processes. By studying the unique characteristics of each ring system, scientists gain clues about the origins of the material that forms rings and the environmental conditions that sustain them. Theories about ring origins have evolved significantly over time. While early astronomers once believed rings might be the remnants of shattered moons, newer theories suggest a more complex picture. Some rings may have formed from material left over from the planet's formation, while others could be the result of gravitational interactions that have trapped dust and ice particles over billions of years. Additionally, collisions between moons, asteroids, or comets could create the initial debris needed for a ring system to form. Saturn's rings, in particular, are thought to have formed when a large moon or icy body was torn apart by Saturn's gravity. A fascinating hypothesis involves the concept of frost lines, which are regions in a solar system where temperatures are low enough for volatile compounds like water, methane, and ammonia to condense into ice. In our solar system, the frost line is located between the orbits of Mars and Jupiter. This region might help explain why Saturn's rings are primarily composed of water ice, while the rings of Uranus and Neptune contain darker, carbon-rich materials. The frost line theory suggests that planets forming beyond this line are more likely to accumulate icy rings, while those within the line might have rings with different compositions. As scientists continue to explore these mysteries, one of the most exciting frontiers is the possibility of artificial ring creation. Could humans one day create rings around Earth or other planets as part of space engineering projects? This concept, known as Astroengineering, is still purely speculative, but it represents the bold spirit of exploration that has always driven humanity to seek answers about the cosmos. In theory, creating a ring around a planet could be a means of conducting scientific research, managing solar energy, or even shielding a planet from cosmic radiation. While this idea remains far in the future, it exemplifies the curiosity that planetary rings inspire, and the boundless imagination they ignite in those who study them. The allure of planetary rings lies not only in their beauty but in the profound questions they raise about the forces that shape the universe. From their formation to their composition and eventual fate, rings are an enduring mystery that scientists are only beginning to unravel. Their complexity speaks to the intricate balance of gravitational and electromagnetic forces that govern the cosmos, revealing the delicate interplay that sustains these majestic structures. As we continue our journey of discovery, the rings of Saturn, Jupiter, Uranus, and Neptune serve as reminders of the vast and interconnected nature of our universe. They offer glimpses into processes that may shape other planetary systems and inspire us to look beyond our own world in search of answers. In studying these rings, we come closer to understanding not only the history of our own solar system but the broader principles that govern the cosmos, from the smallest particles to the grandest celestial bodies. Whether we are examining the icy rings of Saturn or contemplating the possibility of ringed exoplanets, the study of planetary rings is a testament to the endless curiosity that drives scientific exploration. Each discovery brings us a step closer to understanding the complex tapestry of forces that bind our solar system together and, in turn, helps us comprehend our place within the vast and mysterious universe. These spectacular rings are not just mere decorations around planets but act as natural laboratories where cosmic forces like gravity, magnetism, and angular momentum play out on a grand scale. The thin, disc-like structures are composed of countless particles ranging in size from tiny grains to massive chunks of ice and rock. Each of these particles orbits the planet independently, creating a beautiful and intricate dance dictated by precise physical laws. By observing how these particles move, interact, and even collide, scientists can better understand the principles that govern celestial mechanics not only in our solar system but across the cosmos. The study of rings also raises questions about the environmental conditions that sustain or hinder their formation. For instance, radiation from the sun plays a role in altering the surfaces of ring particles over time, gradually aging them through exposure. This process is especially evident in Saturn's rings, where sunlight, cosmic rays, and particles from the solar wind can alter the ring's icy surfaces, giving them a darker and potentially reddish hue. Through this slow transformation, scientists can estimate the ages of various regions within the rings and perhaps deduce whether they are remnants of ancient events or more recent phenomena. Recent observations have also shown that the particles in Saturn's rings are organized into waves and structures created by the gravitational influence of Saturn's moons, known as shepherd moons. These moons travel along or near the edges of rings, stabilizing their structure and preventing particles from dispersing into space. The moons also create fascinating phenomena, such as propeller-shaped patterns within the rings, caused by the gravitational forces exerted by hidden moonlets, or smaller moon-like objects embedded within the rings. These interactions illustrate a delicate cosmic balancing act, where even the tiniest celestial bodies play crucial roles in shaping the larger structures around them. The Cassini spacecraft's mission to Saturn provided a groundbreaking wealth of information about these rings, offering close-up images that revealed structures smaller than ever before observed. Among the most intriguing discoveries were the narrow, dense features known as ringlets, which resemble grooves etched into the rings. Scientists are still unraveling how these ringlets form, with theories suggesting that they result from the repeated clumping and breaking apart of ring particles, influenced by Saturn's gravity and the presence of nearby moons. Cassini also detected temperature variations across Saturn's rings, revealing that ring particles exhibit different thermal behaviors depending on their size and composition. Larger particles retain heat longer, cooling down more slowly than smaller ones, which helps researchers infer their relative sizes and densities. This temperature data has been invaluable for understanding the physical properties of ring particles, and scientists are continually refining models that describe how these particles behave under varying temperatures and environmental conditions. One of the mysteries surrounding planetary rings involves their long-term stability. Despite their majestic appearance, rings are thought to be transient structures, subject to gradual decay over millions or billions of years. Observations suggest that Saturn's rings are losing material at a rate that could cause them to disappear in another 100 million years, a blink of an eye in cosmic terms. This dissipation process is influenced by multiple factors, including the constant bombardment by micrometeoroids, the effects of solar radiation, and the gradual ring rain phenomenon previously mentioned. The loss of ring material through ring rain is particularly fascinating because it suggests that Saturn's rings are essentially recycling material into the planet's upper atmosphere. Particles spiraling inward along magnetic field lines are deposited into Saturn's ionosphere, where they interact with atmospheric gases and produce a subtle, shimmering aurora. This process not only affects the planet's atmosphere but may also help explain why Saturn's rings are unusually bright compared to the darker, more carbon-rich rings of Uranus and Neptune. If Saturn's rings are indeed relatively young, their bright, icy composition could be evidence of a more recent formation event, possibly involving a large, icy moon that was shattered by a collision. Theories about the origin of Saturn's rings abound, but a few primary ideas dominate scientific discourse. One hypothesis is that the rings formed from the remnants of a moon that wandered too close to Saturn and was torn apart by tidal forces, a process known as Roche limit fragmentation. When an object crosses this threshold, the gravitational pull of the planet is strong enough to overcome the object's structural integrity, causing it to disintegrate. The resulting debris could then be captured into orbit around the planet, forming rings. This theory is supported by the proximity of Saturn's rings to the planet itself, as they lie well within Saturn's Roche limit, where tidal forces dominate over the self-gravity of large objects. Another hypothesis is that the rings could be leftover material from the early solar system, a remnant that never coalesced into a larger moon or was prevented from doing so by Saturn's strong gravitational field. This idea implies that the rings are as old as the planet itself, meaning they have been continuously shaped and reshaped by cosmic forces for billions of years. However, the relatively pristine appearance of Saturn's rings suggests a much younger age, potentially challenging this theory unless some process continually refreshes the ring material to keep it bright and icy. These competing theories underscore the complexity of studying planetary rings, as each ring system appears to have its unique history and characteristics. The rings of Uranus and Neptune, for instance, are darker and much less massive than Saturn's, hinting that different processes may have influenced their formation and evolution. The faint rings of Neptune, only confirmed in the late 1980s, are believed to consist of dust and ice particles that could have originated from impacts on the planet's moons. Unlike Saturn's bright, icy rings, the rings of Uranus and Neptune contain more carbon-rich material, possibly indicating a different origin or longer exposure to radiation that darkened their surfaces. The rings of Jupiter are particularly enigmatic, consisting of a thin, faint halo of microscopic particles likely created by impacts on its innermost moons. These rings lack the dense structure and intricate patterns seen around Saturn, suggesting that Jupiter's intense gravitational field and rapid rotation create a more turbulent environment where particles are more easily dispersed. The thinness of Jupiter's rings may also be a result of strong magnetic fields that sweep away small particles, leaving only the finest dust to form the rings we see today. Looking beyond our solar system, scientists are increasingly interested in the potential for rings around exoplanets. Observations of distant star systems have already revealed hints of ring-like structures around young, forming planets, and future telescopes may be able to confirm these suspicions. Detecting rings around exoplanets would provide valuable clues about the formation and stability of planetary rings on a much broader scale, potentially revealing universal patterns in how these structures arise and evolve. One of the most tantalizing possibilities in exoplanetary research is the detection of rings around super-Earths or other rocky worlds, which could defy our current understanding of ring formation. Discovering rings around planets beyond gas giants would force scientists to rethink the conditions under which rings can exist and explore new explanations for their origins. For instance, could rings form around a terrestrial planet with a powerful magnetic field or an unusual rotational speed? Such findings would challenge existing theories and expand our knowledge of planetary science. In the context of astrobiology, planetary rings could also play a role in the habitability of moons orbiting gas giants. Rings can influence a moon's climate by reflecting sunlight and creating a more stable thermal environment. Additionally, particles from the rings could fall onto a moon's surface, delivering organic material that might contribute to prebiotic chemistry. While this concept remains speculative, the idea that rings could support life indirectly through their interactions with nearby moons adds another layer of intrigue to the study of these structures. As we look further into the cosmos, the mysteries of planetary rings will continue to captivate and challenge scientists. With each new mission, telescope, and model, our understanding deepens, but the full story of these enigmatic structures remains just out of reach. They are a reminder of the dynamic and often unpredictable nature of the universe, where beauty, complexity, and mystery coexist in perfect harmony. And while we may never fully unlock all the secrets of planetary rings, each discovery brings us a step closer to understanding the cosmic forces that shape not only our solar system but the entire universe. The cosmic dance of planetary rings reveals an incredible complexity that continues to fascinate astronomers and planetary scientists. The intricate structures within rings, influenced by countless variables like gravitational interactions, moonlets, and magnetic fields, provide a window into the mechanics of the solar system's earliest formation stages. Rings are not only shaped by the massive planets they encircle but also by minuscule moons within or near their boundaries, which either stabilize or distort their configurations. Each planetary ring system within our solar system has distinct characteristics, hinting at varied histories and environmental factors that shaped them over billions of years. For instance, Saturn's iconic rings are dense, expansive, and bright, while the rings of Jupiter, Uranus, and Neptune are fainter, narrower, and often darker. These differences are not just matters of appearance. They reflect diverse processes in ring formation and evolution and provide clues about each planet's unique developmental journey. Scientists speculate that Saturn's rings could indeed be relatively young, possibly formed from a catastrophic collision event that shattered a large moon or icy comet. Such a collision could have created the massive supply of icy debris that we now see as Saturn's rings. In contrast, the darker, more diffuse rings of Uranus and Neptune suggest older structures that have had more exposure to cosmic radiation, which gradually darkens ice and organic material. Alternatively, their composition might inherently differ from Saturn's, originating from dustier, more carbon-rich debris that absorbed and scattered light differently from the outset. Another intriguing theory proposes that Saturn's rings may be rejuvenated, by ongoing processes. This theory suggests that collisions and other interactions between particles could grind down larger pieces into smaller ones, potentially replenishing certain areas with fresh, bright particles, thereby keeping Saturn's rings relatively bright over extended periods. This idea, if validated, would indicate a fascinating cycle of renewal within the ring system that may also occur around other planets, but on a less visible scale. An interesting discovery by the Cassini mission was that Saturn's rings contain organic molecules, compounds rich in carbon and hydrogen. This unexpected finding hints at complex chemical interactions taking place within the rings. Particles from the rings seem to be falling into Saturn's atmosphere, adding these organic molecules into the upper layers of the planet's clouds. This pollution of Saturn's atmosphere by its own rings could provide insight into how gas giants interact with their ring systems, as well as hint at how planets with rings might differ from those without them in both chemical and atmospheric composition. In recent years, the idea of moons acting as shepherds has garnered significant attention in explaining how rings maintain their structure. Shepherd moons, like Prometheus and Pandora around Saturn, create boundary lines in the rings, using their gravitational influence to gather particles into narrow, stable rings and prevent them from spreading too far outward. These tiny moons have a profound influence on the rings, essentially herding particles into place, and even creating gaps or narrow divisions between sections of the rings. For instance, the famous Cassini division in Saturn's rings is maintained in part by the gravitational effects of nearby moons. Without these shepherding forces, the ring particles might drift away, lose their organized structure, or even dissipate altogether over time. Another captivating phenomenon within Saturn's rings is the presence of spokes, mysterious radial features that appear temporarily within the rings. These spokes were first observed by the Voyager spacecraft and later studied extensively by Cassini. They appear as dark, shadowy lines or bright streaks that run across the ring's radial direction and seem to rotate along with the planet. Scientists suspect that the spokes might be caused by electrostatic forces generated by Saturn's magnetic field, which lift tiny dust particles above the ring plane. This effect temporarily disrupts the usual orderly structure of the rings, creating the appearance of these spokes. The exact mechanism remains somewhat mysterious, but the spokes underscore the rich interplay of electromagnetic and gravitational forces at work within the ring system. Recent studies also reveal that rings may serve as archives of the solar system's history, preserving clues about past events, such as asteroid impacts or comet flybys. The ring particles themselves contain ancient materials, and analyzing their compositions could reveal details about the primordial cloud of gas and dust that formed our solar system. As particles collide, shatter, and reassemble over time, they carry with them traces of these processes. Some scientists believe that, through in-depth chemical and isotopic analysis of ring particles, we may even be able to reconstruct the timeline of significant solar system events, like close encounters with massive bodies or migrations of planets within their orbits. The study of planetary rings is not just limited to our solar system. Astronomers are also searching for ring systems around exoplanets, hoping to extend our understanding to alien worlds. The discovery of ring-like structures around young exoplanets offers new opportunities to explore how rings might form under different stellar conditions, perhaps involving exotic materials or unique gravitational forces. Rings observed around other star systems could differ significantly from what we see in our solar system, providing a more diverse array of case studies for planetary scientists to examine. One notable discovery that excited the scientific community came from the observation of the star J1407, which appeared to have a massive ring system orbiting around a planetary mass companion. This exoplanetary ring system, if confirmed, would dwarf Saturn's rings, spanning a distance many times greater and potentially containing thousands of times more material. Observing such rings opens a new chapter in planetary science, as it raises questions about what conditions allow rings of such scale to form and whether they might be stable or simply transient phenomena in the life cycle of planetary systems. The prospect of observing rings in other star systems also raises questions about the potential for ringed moons around exoplanets. Moons in these distant systems could possess their own rings or even contribute material to a host planet's ring system. Observations with upcoming telescopes, such as the James Webb Space Telescope, may offer insights into whether such phenomena exist beyond our solar system. These discoveries would help scientists test and refine their models of planetary ring dynamics on a grander cosmic scale. Planetary rings may also hold key insights into the early formation of planets themselves. Current theories suggest that our own planet and others in the solar system formed from an initial protoplanetary disk of gas and dust that surrounded the Sun. Studying rings as miniature analogues to this original protoplanetary disk allows scientists to explore how dust and gas coalesce into larger structures. By examining how particles and rings cluster together or drift apart, scientists can simulate conditions similar to those in early solar system formation, revealing how planets might grow from tiny seeds of matter over millions of years. Ultimately, planetary rings are far more than decorative bands encircling gas giants. They are dynamic, evolving systems that reflect complex physical, chemical, and even atmospheric interactions. Rings act as barometers for the planets they orbit, giving scientists insights into the past, present, and even the future of these worlds. As we continue to study them, each ring system challenges our understanding, unveiling the elegance and complexity of the universe. The allure of planetary rings lies in their paradoxical nature. They appear so fragile, almost ephemeral, yet they have endured for potentially millions or billions of years. They are both chaotic and orderly, governed by random collisions yet shaped by precise gravitational harmonics. They invite us to look deeper into the mechanics of the universe, raising new questions and, inevitably, inspiring awe. Each discovery about planetary rings opens a new layer of mystery, leaving us with a humbling reminder of the intricate beauty and enduring enigma of the cosmos. As we dive deeper into the science of planetary rings, it becomes evident that these celestial phenomena are not only beautiful but also key to understanding the dynamics of planetary systems. For example, the study of ring systems can illuminate aspects of planetary evolution that are relevant not just to gas giants like Saturn but also to terrestrial planets, moons, and even exoplanets. The dynamic behavior of ring particles is largely influenced by the gravitational interactions with nearby moons and the planet itself. This gravitational ballet creates a rich tapestry of patterns, including gaps, waves, and spirals. The B-ring of Saturn, for instance, exhibits remarkable features like density waves, which arise due to gravitational perturbations from Saturn's moons. These waves propagate through the ring, altering the local density of particles and giving rise to striking visual patterns. Understanding how these waves are generated and maintained helps scientists learn more about the ring's composition and structure, as well as the forces at play within the planetary system. Moreover, the concept of ring dynamics extends beyond mere observation. It also requires a deep understanding of physics, particularly fluid dynamics and orbital mechanics. Ring particles behave somewhat like a fluid, with their collective motion determined by gravitational influences, collisions, and other forces. The interactions among particles can be described mathematically, allowing researchers to create simulations that mimic the real-world behaviors of these ring systems. By studying these models, scientists can predict how rings will evolve over time, including changes in structure due to collisions, gravitational disturbances, and the gradual dispersion of material. Recent advancements in computational power have allowed for increasingly sophisticated simulations of ring dynamics. These simulations can incorporate various factors such as particle size distribution, gravitational influences from the planet and moons, and even the effects of sunlight on the particles themselves. By tweaking these variables, researchers can observe how different conditions affect the stability and longevity of the rings. For instance, some simulations suggest that the rings may be more resilient than previously thought, potentially lasting much longer than just a few 100 million years if conditions are favorable. One particularly fascinating aspect of ring dynamics is the concept of ring viscosity, a measure of how ring particles interact and move with respect to one another. This viscosity can lead to surprising outcomes, such as the migration of particles toward the center of the ring system. This phenomenon, which has been observed in laboratory experiments as well as in simulations, suggests that under certain conditions, rings can self-organize and maintain their structure over extended periods, contradicting earlier assumptions that rings would inevitably dissipate over time. The presence of magnetic fields also plays a significant role in the dynamics of planetary rings. Saturn's magnetic field interacts with charged particles within the rings, influencing their motion and potentially contributing to the formation of features like the aforementioned spokes. Additionally, this interaction can create a unique environment within the rings, where particles experience forces that differ from those in a typical gravitational setting. Understanding these magnetic influences helps scientists better grasp how the rings operate and evolve, as well as how they might differ from rings around other celestial bodies, such as the icy moons of Jupiter. As our observations of rings expand beyond Saturn, a growing body of research is focusing on the rings of Uranus and Neptune. Both of these gas giants possess ring systems that were once thought to be less significant than Saturn's. However, data from the Voyager spacecraft and subsequent observations revealed that these rings, while narrower and less bright, exhibit intriguing features of their own. The rings of Uranus, for instance, contain a series of dark, narrow bands that suggest a different composition and history from Saturn's rings. The existence of such features raises questions about how rings can form and persist under varying conditions, challenging the notion that only large gas giants can support substantial ring systems. Additionally, observations from ground-based telescopes and space missions are beginning to unveil the presence of rings around other types of celestial bodies, including dwarf planets and asteroids. The discovery of rings around the Kuiper Belt object Haumea highlights the possibility that rings could be more widespread in the universe than previously recognized. These findings not only expand our understanding of rings but also suggest that the mechanisms of ring formation and maintenance could operate under diverse conditions across the cosmos. Another key area of research is the interplay between rings and the atmospheres of their host planets. Saturn, for example, has a dynamic atmosphere that undergoes seasonal changes driven by its tilt and distance from the Sun. These atmospheric changes can influence the ring system in various ways, from altering the temperature of ring particles to affecting their chemical composition. As researchers continue to probe this relationship, they gain insights into how planetary atmospheres interact with ring systems, potentially leading to the development of new atmospheric models that account for these interactions. The ongoing exploration of planetary rings also sparks questions about the origins of these captivating structures. Theories suggest that many ring systems may originate from moons or other celestial bodies that were pulled apart by tidal forces as they ventured too close to their parent planet. This process, known as tidal disruption, can create a vast array of ring particles, which may initially be concentrated in a narrow band before spreading out over time. Understanding the mechanisms behind this process is essential for piecing together the history of ring systems and their host planets. Moreover, the study of planetary rings raises philosophical questions about the nature of celestial phenomena. Rings symbolize the complex interplay of forces at work in the universe, offering a reminder of how interconnected different elements of a planetary system can be. They challenge our perception of stability and permanence, illustrating how celestial bodies can undergo dramatic changes over time due to gravitational forces, collisions, and other interactions. In many ways, rings encapsulate the dynamic nature of the cosmos, where chaos and order coexist in a delicate balance. As we gaze at the beautiful rings of Saturn and the more subdued structures of Uranus and Neptune, we are reminded of the mysteries that still linger in our understanding of the universe. The ongoing exploration of these enigmatic systems is not just a pursuit of knowledge, it is an invitation to marvel at the beauty and complexity of the cosmos. With every new discovery, we uncover layers of history, revealing the stories etched in the particles that dance around these massive planets. The science of planetary rings is a testament to human curiosity and our unyielding desire to explore the unknown, reminding us that the universe still holds many secrets waiting to be unveiled. The implications of our understanding of planetary rings extend beyond the solar system. As astronomers observe distant star systems and search for exoplanets, they begin to consider the potential for ring systems around these alien worlds. The study of how rings behave and evolve in diverse environments could offer insights into the formation of planetary systems beyond our own. The discovery of rings around exoplanets, or the identification of similar ring structures around other celestial bodies, will not only enrich our understanding of cosmic dynamics but also enhance our grasp of the processes that shape planetary systems throughout the universe. As we stand on the precipice of new discoveries, the ongoing research into planetary rings promises to unveil further mysteries of the cosmos. The intricate beauty of these structures and the complex physics governing their behavior invite us to explore deeper, fueling our quest for knowledge and inspiring future generations of scientists and astronomers. With every observation, simulation, and analysis, we draw closer to understanding the remarkable phenomena that shape our universe, and in doing so, we uncover not just the secrets of planetary rings but also the very essence of cosmic existence itself. The story of planetary rings continues to unfold, and as we venture further into the cosmos, the questions we ask will guide our discoveries. What forces shape these structures? How do they interact with their host planets? What can they tell us about the history of our solar system and beyond? As we grapple with these questions, we engage with the mysteries that define our existence, reminding us of the interconnectedness of all things in the universe. Ultimately, the exploration of planetary rings invites us to contemplate our place in the cosmos and inspires a sense of wonder about the vast and intricate tapestry of space that surrounds us. As we reflect on the allure of planetary rings, we recognize that they are not merely celestial adornments. They are gateways to understanding the processes that govern planetary formation and evolution. The intricate dance of particles, the gravitational interactions that create stability and chaos, and the connections to atmospheric dynamics all come together to paint a vivid picture of the cosmos. The future of planetary ring research holds the promise of illuminating even more profound mysteries, helping us to unravel the complexities of the universe one ring at a time. The science of planetary rings embodies the quest for knowledge that drives humanity to explore the unknown. As we continue to study these fascinating structures, we unlock the secrets of the cosmos and confront the beauty of existence itself. Each ring system serves as a reminder of the delicate balance that governs the universe, urging us to look deeper into the mysteries that lie ahead. With every discovery, we expand our understanding of the cosmos and our place within it, forging a path toward a future filled with wonder and exploration. As we continue to delve into the mysteries surrounding planetary rings, it is important to consider the broader implications of our research on these fascinating structures. The exploration of rings is not merely a study of aesthetics. It intertwines with fundamental questions about the evolution of our solar system and the potential for life elsewhere in the universe. By understanding the dynamics of rings, we can gain insights into the conditions that allow planets to form and sustain environments capable of supporting life. For instance, the interaction between planetary rings and their host planets can influence atmospheric conditions. The presence of a robust ring system may play a role in the climate dynamics of a planet by modulating solar energy absorption. Additionally, the gravitational influence of rings can affect the orbits of nearby moons, which in turn can have cascading effects on the overall stability of the planetary system. Such relationships emphasize the interconnected nature of celestial bodies, where changes in one component can lead to significant transformations in others. Recent discoveries of exoplanets and their potential ring systems further enrich this narrative. The study of distant worlds may reveal ring systems that differ drastically from those in our solar system, prompting scientists to reevaluate existing theories about ring formation and stability. As telescopes become more advanced, we may witness the unveiling of rings around planets and other star systems, opening a new frontier in our understanding of planetary dynamics. The ongoing analysis of the material composition of ring systems has also revealed intriguing insights into their origins. Many researchers believe that the particles found in rings are remnants of moons or comets that were disintegrated by tidal forces or collisions. This perspective suggests that ring systems are not static but rather dynamic entities shaped by the history of their host planets. In some cases, the recycling of ring material may provide clues about the evolution of the planetary system as a whole. Additionally, the study of ring systems contributes to our understanding of the formation of moons and other celestial bodies. As rings are composed of smaller particles, their interactions can lead to the aggregation of material, potentially forming new moons over time. This process can be observed in the case of Saturn's rings, where simulations indicate that some particles may gradually coalesce to form larger bodies, reflecting the same processes that governed the early solar system. The exploration of icy bodies, such as those found in the Kuiper Belt, also underscores the relevance of ring studies. These distant regions are populated by a variety of small celestial bodies, many of which may exhibit ring-like structures or other features reminiscent of planetary rings. By examining these icy bodies, scientists can gain a broader understanding of how rings might form in different environments, as well as how similar processes might occur in other star systems. One of the most exciting aspects of studying planetary rings is the potential to uncover new physics that could redefine our understanding of celestial mechanics. The behavior of ring particles, influenced by factors such as collision rates, gravitational interactions, and electromagnetic forces, presents a complex and rich landscape for researchers to explore. New discoveries in this area could lead to groundbreaking advancements in astrophysics, helping to answer long-standing questions about the fundamental forces that shape the universe. As we strive to comprehend the origins and dynamics of planetary rings, we must also acknowledge the technological advancements that have made this research possible. Space missions like the Cassini-Huygens mission to Saturn and the ongoing studies of the Voyager spacecraft have provided invaluable data, enhancing our understanding of these celestial phenomena. The wealth of information gathered from these missions has reshaped our perspectives on planetary rings, allowing us to develop more accurate models and simulations. In the coming years, new missions are being proposed that could further illuminate the mysteries of planetary rings. For example, missions targeting the moons of Saturn and Uranus may yield critical insights into the interactions between these celestial bodies and their respective rings. Such missions could involve the deployment of landers or orbiters capable of collecting detailed data about the composition and dynamics of rings, ultimately advancing our knowledge of planetary systems as a whole. Moreover, the study of rings is not limited to gas giants alone. Rocky planets and their potential ring systems are also being investigated. The discovery of rings around small celestial bodies, such as asteroids and dwarf planets, suggests that the mechanisms driving ring formation may be more widespread than previously thought. This revelation opens new avenues for exploration, prompting researchers to consider how rings could influence the evolution of terrestrial worlds and their potential for habitability. In addition to the scientific advancements, the exploration of planetary rings raises important philosophical questions about our understanding of the universe. These structures serve as a reminder of the beauty and complexity inherent in celestial phenomena, urging us to appreciate the intricate relationships that govern planetary systems. As we unravel the mysteries of rings, we are confronted with profound reflections on our own place in the cosmos and the delicate balance that sustains life on Earth. As we continue to investigate planetary rings, we find ourselves at the intersection of science, technology, and philosophy. The ongoing exploration of these mesmerizing structures invites us to ponder the nature of existence itself. Each discovery enhances our appreciation for the universe, revealing the wonders that lie beyond our world. The science of planetary rings, with its rich tapestry of interactions and complexities, serves as a testament to humanity's unyielding curiosity and our quest for knowledge. The study of planetary rings offers a window into the intricacies of the cosmos, revealing the dynamic processes that shape planetary systems. From the gravitational interactions that govern ring dynamics to the potential for new discoveries in exoplanetary systems, the exploration of rings is a testament to the beauty and complexity of the universe. As we continue our journey of discovery, we uncover not only the secrets of planetary rings but also the profound connections that link us to the broader cosmos. In the years ahead, the mysteries of planetary rings will continue to captivate scientists and enthusiasts alike. The ongoing research will not only enhance our understanding of these celestial phenomena but also deepen our appreciation for the intricacies of the universe. The journey into the science of planetary rings is a testament to human curiosity and our relentless pursuit of knowledge, reminding us that the universe still holds many secrets waiting to be unveiled. The exploration of planetary rings invites us to embark on a journey of discovery, urging us to look beyond the confines of our world and embrace the wonders of the cosmos. Each ring system serves as a unique laboratory for understanding the dynamics of celestial bodies, offering valuable insights into the processes that govern the universe. As we continue to explore the beauty and complexity of planetary rings, we forge a deeper connection with the cosmos and, in doing so, expand the horizons of human knowledge. In summary, the study of planetary rings is a multifaceted endeavor that spans across various scientific disciplines, offering a glimpse into the dynamic processes that shape our universe. By investigating the formation, structure, and dynamics of these celestial phenomena, we gain invaluable insights into the forces that govern planetary systems, shedding light on the intricate relationships that exist among celestial bodies. The mysteries of planetary rings continue to unfold, inviting us to explore the cosmos with wonder and curiosity. As our understanding deepens, we are reminded that the universe is a vast and intricate tapestry, woven together by the threads of time, space, and matter. The exploration of planetary rings serves as a poignant reminder of the beauty and complexity that surround us, urging us to embrace the mysteries of the cosmos and the journey of discovery that lies ahead. The quest for knowledge will continue to drive humanity forward, inspiring future generations to look up at the stars and wonder about the universe's secrets. The science of planetary rings will remain a cornerstone of this exploration, inviting us to ponder the origins, evolution, and significance of these captivating structures. With each new discovery, we inch closer to unraveling the mysteries of the cosmos, propelling us into a future filled with awe and possibility. Through the study of planetary rings, we not only uncover the secrets of our solar system but also embark on a journey that transcends time and space. The quest for knowledge continues, fueled by our innate curiosity and desire to understand the universe in which we reside. As we gaze at the rings of Saturn, Uranus, and beyond, we are reminded of the intricate beauty of the cosmos and the profound connections that bind us to the stars. With every observation and every discovery, we enrich our understanding of the universe and our place within it. The science of planetary rings serves as a testament to human ingenuity, curiosity, and the enduring spirit of exploration. As we continue our quest for knowledge, we look to the stars and the wonders that await us, inspired by the beauty and complexity of the celestial realm. The exploration of planetary rings is an enduring journey that intertwines science, discovery, and wonder. As we delve into the intricacies of these mesmerizing structures, we uncover the secrets of the universe, forging a deeper connection with the cosmos and inspiring future generations to embark on their own journeys of discovery. The mysteries of planetary rings beckon us to look beyond the familiar, to embrace the unknown, and to continue our quest for knowledge in an ever-expanding universe. As we delve further into the exploration of planetary rings, it's essential to address the implications of our findings on the broader context of planetary formation and the evolution of celestial systems. The existence of rings is not merely an aesthetic feature. Rather, it offers a glimpse into the chaotic and dynamic processes that have shaped our solar system and potentially other systems throughout the universe. One of the key questions scientists grapple with is why some planets possess prominent ring systems, while others do not. The answer lies in a complex interplay of factors, including a planet's mass, its gravitational influence, and its distance from the Sun. Gas giants like Saturn, Jupiter, Uranus, and Neptune have the necessary gravitational pull to capture and maintain rings composed of various materials, ranging from ice to rocky debris. These planets also have a rich history of interactions with their moons, which can lead to the fragmentation of larger bodies into smaller particles that form ring systems. The process of ring formation is a dynamic and sometimes violent affair. The gravitational forces exerted by a planet can pull apart celestial objects that venture too close, a phenomenon known as tidal disruption. This can lead to the creation of rings composed of smaller fragments from these disintegrated bodies. Saturn's rings are a prime example of this process, where the gravitational interplay between the planet and its moons leads to a constant recycling of ring material. Understanding these interactions provides insight into the historical and ongoing evolution of ring systems. Another fascinating aspect of planetary rings is their composition. The materials found within rings can vary significantly, from icy particles to rocky debris. This diversity is indicative of the origins of the rings and the materials available in a particular planetary system. For instance, Saturn's rings are primarily composed of water ice, which suggests a different formation history compared to the darker, more complex materials found in the rings of Uranus and Neptune. The study of ring composition not only reveals the conditions present during their formation but also allows scientists to infer the processes that shaped the early solar system. Recent advancements in technology and observational techniques have revolutionized our understanding of ring dynamics. High-resolution imaging from missions like Cassini has unveiled intricate details about ring structures, revealing features such as wave patterns and the gravitational effects of nearby moons. These observations have led to new insights into the processes governing ring stability, such as the balance between gravitational forces and the collisions among ring particles. The study of these interactions is crucial for comprehending how rings can persist over billions of years despite the inherent forces that would tend to disperse them. Recent discoveries have also suggested that planetary rings can exhibit surprising behaviors, including the formation of spokes, transient features that appear in Saturn's rings. These spokes are believed to be caused by electromagnetic interactions between ring particles and Saturn's magnetic field. This phenomenon highlights the complex interplay between a planet's magnetic environment and its ring dynamics, adding another layer of complexity to our understanding of these systems. The study of ring systems extends beyond our solar system, with exoplanetary research offering intriguing possibilities for discovering rings around distant worlds. Observations of exoplanets have revealed some candidates that may host ring systems, challenging our understanding of how rings can form and persist in various environments. This exploration could reshape our views on planetary systems and the conditions necessary for the formation of rings. The quest to understand the dynamics of planetary rings is not limited to their formation, it also encompasses their potential fate. The life cycle of a ring system can be a fleeting phenomenon, as the gravitational forces acting on ring particles can lead to eventual dispersal. Over time, the particles may collide, coalesce, or be pulled into their host planets, effectively reducing the size of the rings. The process of accretion and collision within rings mirrors the early stages of planetary formation, serving as a living laboratory for scientists to study these fundamental processes. As we reflect on the significance of planetary rings, it becomes evident that they serve as a lens through which we can examine the broader processes governing the universe. The exploration of rings prompts us to consider questions about the origins of planetary systems, the interactions between celestial bodies, and the potential for life in the cosmos. Rings are not merely decorative features. They represent the intricate dynamics of the universe and our ongoing quest to understand it. The implications of ring studies extend into astrobiology as well. The existence of ring systems can influence the habitability of moons that orbit gas giants. For instance, the gravitational interactions between a planet, its rings, and its moons can create environments conducive to maintaining atmospheres or supporting subsurface oceans, as is theorized for some of the moons of Jupiter and Saturn. These conditions could be critical for the development of life, highlighting the interconnectedness of ring dynamics and astrobiological potential. As we continue to explore planetary rings, we must also consider the cultural and philosophical implications of these studies. The beauty of planetary rings has inspired art, literature, and scientific inquiry throughout history. The awe they inspire serves as a reminder of humanity's connection to the cosmos and our enduring curiosity about the universe. As we unveil the secrets of rings, we are not just expanding our scientific knowledge, we are also deepening our understanding of our place within the greater tapestry of existence. The science of planetary rings encompasses a vast array of topics, from their formation and dynamics to their implications for planetary systems and the potential for life. The study of rings is a testament to human curiosity and the unrelenting pursuit of knowledge. As we gaze upon the magnificent rings of Saturn and other gas giants, we are reminded of the complexity and beauty of the universe. The exploration of planetary rings invites us to look beyond our immediate surroundings, inspiring future generations to continue the journey of discovery. The mysteries of planetary rings are far from fully understood, and ongoing research will undoubtedly reveal new insights that challenge our existing paradigms. As technology continues to advance, we can anticipate a new era of discovery in the study of planetary rings, one that will further illuminate the dynamic processes that govern celestial systems. The future of planetary ring research holds exciting possibilities. As our observational techniques improve, we may uncover even more complex structures and behaviors within rings, reshaping our understanding of how these systems function. The continued exploration of the outer solar system, as well as the study of exoplanets, will provide valuable data that can inform our theories about ring formation and dynamics. Ultimately, the study of planetary rings transcends mere scientific inquiry. It reflects humanity's desire to understand the cosmos and our place within it. Each new discovery serves as a reminder of the beauty and complexity of the universe, urging us to embrace the mysteries that lie beyond our world. The journey into the science of planetary rings is a testament to our curiosity and our unyielding pursuit of knowledge, inviting us to explore the wonders of the cosmos with open minds and hearts. As we continue our exploration of planetary rings, we are not only uncovering the secrets of these celestial phenomena but also deepening our appreciation for the intricacies of the universe. Each ring system tells a story, a narrative woven through time and space that connects us to the cosmos. The mysteries of planetary rings will continue to inspire generations of scientists, artists, and thinkers, fostering a sense of wonder and inquiry that defines the human experience. Through the lens of planetary rings, we glimpse the dynamic interplay of forces that shape the universe, revealing the delicate balance between chaos and order. The study of rings invites us to reflect on our own existence and the interconnectedness of all things. As we seek to understand the origins and dynamics of these captivating structures, we embark on a journey that transcends the boundaries of science, art, and philosophy. The exploration of planetary rings is a testament to humanity's quest for knowledge and our unrelenting curiosity about the universe. The beauty and complexity of these structures invite us to look up at the stars and wonder about the forces that shape our world. As we delve deeper into the science of planetary rings, we celebrate the spirit of exploration that defines our species, embracing the mysteries of the cosmos and the profound connections that bind us to the universe. The science of planetary rings is a captivating journey that continues to unfold, revealing the intricacies of celestial dynamics and the potential for discovery beyond our own solar system. The mysteries of these enchanting structures beckon us to explore, inquire, and reflect on the wonders of the universe. With each new discovery, we expand our understanding of the cosmos and our place within it, forging a deeper connection with the vastness that surrounds us. As we gaze upon the rings of gas giants, we are reminded of the beauty of scientific inquiry and the endless possibilities that lie ahead. The science of planetary rings will continue to inspire and intrigue, guiding us on our journey of exploration as we seek to unveil the secrets of the universe, one ring at a time. Continuing our exploration of the science of planetary rings, it's crucial to delve deeper into the varied mechanisms that contribute to their formation and the intricacies of their evolution. We are reminded that these rings are not static entities. Rather, they are dynamic systems undergoing constant change influenced by a multitude of factors, including gravitational interactions, collisional processes, and the intrinsic properties of the materials that comprise them. The gravitational influence of a planet is a fundamental aspect that governs the behavior of its rings. For instance, in the case of Saturn, its large mass creates a strong gravitational field that can maintain the delicate balance required for the rings to persist. However, this same gravitational pull can also lead to the creation of gaps and divisions within the rings, known as Cassini divisions, which are caused by the gravitational interactions with Saturn's moons. The discovery of these gaps, particularly the well-known Cassini division between the A and B rings of Saturn, showcases the intricate interplay between planetary bodies and their ring systems, providing a tangible example of the gravitational sculpting that occurs within these celestial formations. As we investigate the material composition of rings, we find that the particles vary in size, ranging from microscopic grains of dust to larger chunks of ice and rock. This variation contributes to the complexity of the ring systems and influences their physical properties. For instance, the size distribution of particles can affect the overall reflectivity of a ring, which in turn can provide clues about its composition. The study of particle sizes and their interactions also reveals much about the processes that govern ring dynamics. Smaller particles tend to collide more frequently, leading to a higher likelihood of fragmentation and the creation of additional dust, while larger particles may coalesce, leading to the formation of larger bodies within the rings. One particularly intriguing aspect of ring dynamics is the phenomenon of ring instability. Over time, ring particles can experience gravitational interactions that lead to instabilities, causing waves and spirals to form. These features are not merely visual, they are indicative of the underlying physical processes at work within the rings. Such instabilities may arise from the gravitational influence of nearby moons, leading to the creation of wave patterns that ripple through the rings. These waves are fascinating because they provide valuable insights into the mass and orbital characteristics of the moons influencing them, as well as the overall health and stability of the ring system. Moreover, recent observations have unveiled a new layer of complexity regarding the interaction between rings and their host planets. For example, researchers have discovered that the magnetic fields of gas giants play a significant role in shaping the behavior of ring particles. Charged particles within the rings can experience electromagnetic forces that alter their trajectories, leading to unique phenomena such as the previously mentioned spoke formations observed in Saturn's rings. These interactions underscore the importance of considering not just gravitational dynamics, but also electromagnetic forces when studying the behavior of ring systems. The exploration of rings also raises fundamental questions about the origins of these celestial features. Theories regarding the formation of planetary rings have evolved significantly, especially in light of new data from missions such as Cassini. While earlier models suggested that rings might form from the remnants of a larger moon or asteroid that was shattered by tidal forces, more recent evidence points to the possibility that some rings could have originated from the debris left over from the planet formation process itself. This perspective emphasizes the idea that rings may serve as a snapshot of a planet's formative years, encapsulating the materials and processes that were present during the early solar system. Another avenue of exploration involves the study of transit rings that have been observed around other celestial bodies. Recent research indicates that certain small moons or asteroids can exhibit temporary ring structures due to similar tidal disruption processes. These ephemeral rings can provide valuable information about the conditions necessary for ring formation and the potential for rings to exist around a wider variety of celestial objects than previously thought. By examining these transient phenomena, scientists can glean insights into the broader mechanisms that govern the creation and evolution of ring systems. As we shift our focus to the implications of these discoveries, it becomes apparent that studying planetary rings is not merely an academic exercise. It holds the potential to revolutionize our understanding of planetary systems as a whole. For example, the dynamics observed in ring systems could serve as analogues for the processes at play in the formation of other celestial structures, such as protoplanetary disks surrounding young stars. Understanding how rings evolve in response to various forces may provide critical insights into the processes that lead to the formation of planets and moons in other systems, expanding our knowledge of planetary evolution throughout the galaxy. Furthermore, the implications of ring dynamics extend to the search for extraterrestrial life. The presence of rings around gas giants can influence the habitability of their moons, as previously mentioned. For example, moons located within or near the ring systems may experience increased radiation or tidal heating, which could create environments conducive to hosting life. The study of ring dynamics allows scientists to refine their models of habitability and to identify targets for future astrobiological exploration, contributing to our ongoing quest to discover life beyond Earth. The beauty and complexity of planetary rings are not only captivating but also serve as a reminder of the interconnectedness of all things in the universe. The study of these celestial features encourages us to reflect on our place within the cosmos and to appreciate the intricate web of interactions that govern the behavior of celestial bodies. As we unravel the mysteries of planetary rings, we gain not only scientific knowledge but also a deeper appreciation for the universe's complexity and beauty. The journey of exploration into planetary rings is ongoing, with future missions promising to unveil even more secrets. The potential for new discoveries, particularly as technology advances, is exhilarating. As scientists develop more sophisticated instruments and techniques for observing these distant worlds, we can anticipate a wealth of new data that may challenge existing theories and open new avenues of inquiry. The future of ring research holds the promise of expanding our understanding of the solar system and beyond, shedding light on the processes that shape planetary systems throughout the universe. It is essential to acknowledge the profound impact that studying these celestial phenomena has on our understanding of the universe. Rings serve as a window into the dynamic processes that govern planetary systems and offer critical insights into the origins and evolution of celestial bodies. Each new discovery enriches our knowledge and ignites our curiosity, encouraging us to continue our quest for understanding in the vastness of space. Through the lens of planetary rings, we are reminded of the beauty of scientific inquiry and the importance of asking questions about the universe around us. The mysteries of rings invite us to explore, to challenge our assumptions, and to seek answers to the questions that have captivated humanity for generations. The study of planetary rings is more than just an exploration of celestial structures. It is an exploration of our place in the cosmos and our enduring pursuit of knowledge. In essence, the science of planetary rings encapsulates the essence of humanity's quest for understanding. The intricate dynamics of rings, their formation, and their influence on celestial bodies underscore the complexities of the universe and our connection to it. As we gaze up at the night sky, we are reminded that each ring system tells a story, a narrative woven through the fabric of time and space, waiting to be unraveled by those curious enough to seek the truth. With each new discovery and every advancement in technology, we deepen our appreciation for the wonders of the universe, enriching our understanding of the cosmos and our place within it. The exploration of planetary rings will continue to inspire and intrigue, leading us to question, discover, and dream about the infinite possibilities that lie beyond our own planet. As we look ahead to the future of planetary ring research, we are filled with anticipation for the discoveries yet to come. The mysteries of the cosmos beckon us to explore further, pushing the boundaries of our understanding and igniting our imagination. Each ring, each particle, and each dynamic interaction serves as a reminder of the beauty and complexity of the universe, inviting us to embark on a journey of exploration and discovery that is boundless. In summary, the science of planetary rings offers a fascinating glimpse into the dynamic processes that govern our solar system and beyond. The exploration of these celestial structures not only enriches our understanding of planetary systems, but also enhances our appreciation for the complexity of the universe. As we continue to study planetary rings, we embrace the spirit of inquiry that defines humanity, and remain inspired by the endless mysteries that await us in the cosmos. Continuing our exploration of the science of planetary rings, we must further examine the influence of various environmental factors on these remarkable structures. Beyond the gravitational and electromagnetic forces we have discussed, the impact of space weather, particularly solar radiation and cosmic rays, plays a crucial role in the evolution and characteristics of planetary rings. Space weather and ring dynamics. Space weather, which encompasses the environmental conditions in space resulting from solar activity, has significant effects on the particles within planetary rings. For instance, solar wind, which consists of charged particles emitted by the sun, can interact with the icy and rocky constituents of rings. This interaction can lead to a process known as space weathering, where the surfaces of ring particles undergo alterations due to bombardment by high-energy particles. This not only affects the color and reflectivity of the rings but can also influence their thermal properties and cohesion, potentially leading to fragmentation and altering the dynamics of the ring system. Moreover, cosmic rays, high-energy particles originating from outside the solar system, can also induce chemical reactions in the materials making up the rings. Such reactions may lead to the formation of complex organic molecules, adding another layer of complexity to the study of ring dynamics. The presence of these organic compounds might indicate that the processes that govern the formation of life could have analogues in the environments surrounding gas giants, suggesting that the study of rings could also provide insights into astrobiological possibilities. The role of small moons and shepherding. As previously mentioned, small moons play a significant role in the structure and dynamics of planetary rings. These so-called shepherd moons can exert gravitational forces that help maintain the ring's sharp edges and structures. For example, the moons Prometheus and Pandora act as shepherds for Saturn's F ring, influencing its shape and stability through their gravitational interactions. Their presence prevents the ring material from dispersing into space and creates gaps or waves in the ring structure. These moons not only help maintain the rings but also contribute to the complex dynamics observed within them. The gravitational tug-of-war between the moons and the ring particles can result in fascinating phenomena, such as the formation of spiral patterns, which are visible in high-resolution images taken by spacecraft like Cassini. Observations of these interactions help scientists understand the mass distribution of the moons and their influence on the rings over time, showcasing a delicate balance of gravitational forces. Recent discoveries in planetary ring science. Recent observations and data from missions such as the Cassini spacecraft have transformed our understanding of planetary rings, revealing intricate details about their composition, structure, and dynamics. For instance, the discovery of transient features such as spokes within Saturn's rings, dark radial features that appear and disappear, has puzzled scientists. These spokes are believed to be composed of fine particles that are influenced by the planet's magnetic field. Understanding the formation and disappearance of these spokes provides further insight into the complex interactions between magnetic fields and ring particles, highlighting the need for continued observation and study. Furthermore, Cassini's extensive data collection during its mission has led to breakthroughs in understanding the composition of the rings themselves. Spectroscopic analysis has revealed that the rings are primarily composed of water ice, with varying amounts of silicate and organic materials. This composition is critical not only for understanding the origins of the rings but also for assessing the potential for future exploration. The icy nature of the rings suggests that they may contain essential building blocks for life, raising questions about the potential for resource utilization in future space missions. Why some planets have rings while others do not? One of the most compelling questions in planetary science revolves around the factors that determine why some planets possess rings while others do not. The key to this mystery lies in a combination of factors, including a planet's size, its gravitational influence, the presence of nearby moons, and its location within the solar system. Gas giants, such as Saturn, Jupiter, Uranus, and Neptune, tend to have more prominent ring systems due to their substantial gravitational fields, which can capture and retain ring material. In contrast, terrestrial planets like Earth and Mars lack such massive ring systems, primarily because their weaker gravitational fields are less capable of holding on to the debris necessary to form and sustain rings. Moreover, the proximity of these planets to the Sun may also play a role. The inner solar system is characterized by higher temperatures, which can lead to the sublimation of icy materials that are crucial for ring formation. Another significant aspect influencing the presence of rings is the interaction with moons. The gravitational influence of nearby moons can either contribute to the formation of rings by disrupting larger bodies or hinder ring formation by clearing out debris through tidal forces. In systems where moons are present, the gravitational dynamics become more complex, leading to the formation of intricate ring structures and gaps, as we see in Saturn's rings. The future of ring studies. Looking ahead, the study of planetary rings is poised for exciting advancements, particularly with the development of new observational technologies and missions. Upcoming missions to gas giants, such as NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer, JUICE, while primarily focused on their moons, will also yield valuable data about the ring systems of these planets. These missions will enhance our understanding of the dynamics of rings and their potential interactions with moons and other celestial bodies. Additionally, advancements in ground-based telescopes and space observatories will enable scientists to observe rings around exoplanets. The discovery of ring systems beyond our solar system could significantly broaden our understanding of how common rings are in the universe and what factors contribute to their formation. Such discoveries may lead to a deeper understanding of planetary system evolution, potentially reshaping our theories of planet formation and migration. Moreover, the study of rings may also intersect with the search for extraterrestrial life. Understanding the conditions that foster ring formation can provide insights into the environments surrounding gas giants and their moons, which may harbor conditions suitable for life. By exploring the intricate connections between rings, moons, and their parent planets, we expand our knowledge of habitability in diverse cosmic settings. Conclusion. In conclusion, the science of planetary rings offers a captivating glimpse into the dynamic processes that govern our solar system and beyond. The study of these celestial structures not only enriches our understanding of planetary systems, but also enhances our appreciation for the complexities of the universe. As we continue to investigate the origins, dynamics, and interactions of planetary rings, we embrace the spirit of inquiry that defines humanity, and remain inspired by the endless mysteries that await us in the cosmos. The future of planetary ring research is bright, promising new discoveries that will undoubtedly challenge our current understanding and fuel our curiosity. As we stand on the brink of new explorations and advancements in technology, we must remember that each ring system is not merely a collection of particles. It is a narrative woven through the fabric of time and space, waiting to be unraveled by those curious enough to seek the truth. Through the lens of planetary rings, we are reminded of the beauty of scientific inquiry and the importance of asking questions about the universe around us. The mysteries of rings invite us to explore, to challenge our assumptions, and to seek answers to the questions that have captivated humanity for generations. The study of planetary rings is not just an exploration of celestial structures. It is an exploration of our place in the cosmos and our enduring pursuit of knowledge. We must acknowledge that the journey is far from over. With every observation, every data set, and every new mission launched into the depths of space, we take one step closer to unraveling the complex tapestry of our universe. The mysteries of planetary rings beckon us to venture forth, to uncover the secrets they hold, and to continue our quest for understanding in the vastness of space. The allure of planetary rings lies not only in their beauty, but also in their complexity, and the insights they provide into the workings of our universe. The scientific community's ongoing dedication to unraveling these mysteries ensures that the story of planetary rings will continue to evolve, revealing new layers of understanding and inviting future generations to engage in the timeless pursuit of knowledge. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.